Okay, so 10.1 talks about first just an introduction to 3D solids, and then we'll get into the actual surface areas on 10.2 for prisms and cylinders. So here's the first vocabulary word, polyhedron. You can hear the word poly when you hear that word, so hopefully that reminds you of the word polygon, because it's a solid that's bounded by polygons called faces. So when you have polygons, those are like shapes like a triangle is a polygon, a rectangle, a quadrilateral, even a pentagon, a hexagon, octagon. All of those are different types of polygons, and so we can call them faces that create this 3D solid, or a polyhedron. And it encloses it into a single region of space. Okay, so faces is another vocab word that you're going to want to know about, because it's like how many actual sides to the shape that we have. So it helps to look at something like a cone or a cube, and this right here is a face, right? And so a cube has 6 faces to it. If you count as many faces all the way around, that's called a face. And they're made up of squares, and squares are polygons. Okay? The second vocabulary word is an edge. An edge of a polyhedron is a line segment that's formed by the intersection of 2 faces. So again, it helps to see this visually. Here's my cube. An edge would be these edges here along the square, because they're meeting 2 faces together, so that when I meet the 2 faces, I have an edge. Okay, so an edge is a line segment. It's like just from here to here. That's considered an edge. And so sometimes a question will say, how many edges does this 3D solid have? Definitely helps when you can hold it in your hand and actually count. Or you can kind of just like think about it visually and abstractly and kind of count it in your head. Okay, here's the next one. A vertex, I know you've heard that word before, but a vertex of a polyhedron is a point. And it's a point where 3 or more edges meet. So like, let's look at this. We have, remember there's an edge, like let's say this edge here, this edge, and this one here. That point right there is considered a vertex. All of these points here that create this cube are going to be vertexes. So you have like 4 on the top here, 4 on the bottom there. That's a total of 8 vertex or vertices that this cube has. Okay, and then today, right now, we're about to kind of give it different names of these 3D solids. So it says we can create 3-dimensional objects by transforming 2-dimensional objects. So basically starting with something flat, 2-dimensional, and somehow creating it into a 3-dimensional object. The easiest one to think about is imagine a cardboard box. Remember, everyone gets like a package from Amazon or wherever, and it comes in this like cardboard box. That's a rectangular prism. But at one point, that if you're trying to, like, say, recycle that box, or at one point before that box was created, it was originally flat. It was 2-dimensional before they kind of figured out how to give it that depth so you can actually package it. That's what we're about to discuss here, about like how did it start off first from 2-dimension and work its way to 3-dimension. So we're going to fill in some missing information here about the name of the solid, the definition for it, and how we transform it from a 2-dimensional object. And we can even draw a picture, or maybe a picture will be included for us for each of these solids. Because although we are not finding the surface area for a couple of them, you should still know how we can create all of them, and you should know the names of them all. So here's the first one. And let me get an example just so you can see at the same time. This is an example of, not exactly of this picture here, but this is also called a prism. So the name of this is prism. But prisms can have lots of different shapes attached to it. So here's actually another one. This picture shows a triangular prism. Notice a triangle here and on the other side of it. This is another triangle. So it says it's a polyhedron with 2 congruent faces that are called bases that lie in parallel planes. So what that's telling me here is that if you see 2 of the same shape being parallel to each other, like if you notice here, there's 2 triangles on this end being parallel to each other, and on this one there's 2 squares or rectangles being parallel to each other, because you could imagine this being parallel to the back of it, and so on. Those are called prisms, anytime you have 2 parallel bases. Well, if the picture is showing a triangular prism here, you can technically have other kinds. I'm going to name it right here, triangular prism. we can name prisms by whatever the base is that you see. So if I see two triangles that are being parallel to each other, those are my triangular bases, and I'm going to call it a triangular prism. What if these triangles instead were pentagons or octagons or any other shape that is a polygon? You can name it with that. So there's such a thing as like a pentagonal prism, an octagonal prism, a hexagonal prism. Those are all different words that we can say for different types of prisms. A cube is technically a type of prism because they're just squares that are made up of the same thing. So instead of rectangles, there's cubes. The most basic form, though, is your rectangular prism. That's where you have like all rectangles that are made up of. This one technically shows you a square, though, but imagine if it was a rectangle on every single side, then that's a rectangular prism. Okay, so how do we actually transform this? Well, imagine starting off with one of the bases, like just the triangle or just the square or just the rectangle. If you just started off with one, you would need to translate that triangle until it ended up on the other side of it, right? So that it's parallel to each other. So this will say translate a triangle. In this scenario, because we have a triangular prism, we are specifically starting off with the triangle as your pre-image, essentially, and then translating it over to a certain amount to get to your image, essentially. Okay. Anybody have any questions on prisms? Because there's just one example so far. Yeah. Next one, the next shape, which we're going to learn more about on Monday, is a pyramid. And just like prisms, pyramids can have different types as well. So let me see if I have a picture here. A model of one. This is a pyramid. It's got at the bottom, if you see here, a square at the bottom, and then it's made up of triangles, specifically 4 triangles that meet up at a common point here. So the key words for this polyhedron, the main thing here is that there's no curves. Of all the shapes I've shown you so far of these 3D solids, they're all made up of like line segments, actual edges that you can see. There's no curves to anything, no circles. We're going to eventually see ones that can have curves. But right now, the pyramid is a polyhedron in which the base is a polygon. So it could be a square, it could be a rectangle, it could be a triangle, octagon, hexagon, pentagon, so many choices here. Let me see if I have any other, nope, I don't have any other cones here. But at some point I'll put some examples up so you can see other examples. This is considered, because this is a square right here, this would be called a square pyramid, which is what we're going to try to draw here. I'm going to write this down, square pyramid. And here's the rest of the definition. In addition to the base, it says the lateral faces. Lateral means the sides. All of the sides, the faces that are on here, are going to be triangles. And there will be the same number of triangles as the polygon's side length. So for example, a square has 4 sides. That means there's got to be 4 triangles here. If the base that I was working with instead of a square was a pentagon, that would have 5 triangles because a pentagon has 5 sides. Octagon has 8 sides, so that would have 8 triangles. And that would be hard to draw, of course, so we're going to just try to draw just a square pyramid. Again, I am not artistic, so I'm doing the best I can. You might have a way better diagram than I do, but imagine having a square to start with. Okay, and it says here's how you could transform this into a pyramid. You would start with the square, and if you notice here, there's a bunch of squares stacked on top of this, but at different sizes. So there's like the biggest square on the bottom, and then as you keep getting more and more higher, it keeps putting smaller and smaller rectangles on top of it until you get to the very top, and there's just a little tiny point left. So this is where you dilate or reduce specifically a square. You keep doing that until it's like non-existent, it's just a dot. And so here's where I want to draw my square with 4 triangles coming up to a common point. You can decide where your common point is. I'll just do it up here. So you have like one triangle here, here's another one, and another one. It's just hard to see the overlap there because it's on its side, essentially. But the square has to be the base, one square. That's the difference between a prism and a pyramid. Prisms have 2 bases that are parallel to each other. A pyramid just has the one, and it could be, again, any polygon that we're working with. All right, anybody have questions on that one? So then we have these things that are called non-polyhedral solids. That means that now you're getting into some curves or circular objects because they're not polygons. Polygons can include circular things. So the first one we're going to talk about is a cylinder. And let me show you what a cylinder looks like. You probably have definitely seen one of these in real life. It's like a Coke can. Anytime you see where it's got like a circular top and a circular bottom, but then the rest of it is, it's obviously going to be rounded when the rest of it is created, but it's almost as if it's like a rectangular, sort of curved rectangular piece around the two circles. So it's a solid with congruent circular bases. So keywords there, congruent circular bases that lie in parallel planes. The circles have to be parallel to each other. You could look at it from top and bottom or side to side, but you're always going to have two parallel circles for a cylinder. Okay, now how do we create that? Well, there's a lot of different ways to think about how to create it. The first option would be you could translate a circle, just similar to how we created the prism, right? Take whatever the base is and translate that circle over and over again, like to every single spot up until it got to the next spot at the very top, for example, from the bottom to the top. The size of the circle is not changing, so there's no dilations here. It's just moving it from the bottom to the top. Or another way to think about it is that you're stacking a bunch of circles on top of each other to fill in that entire amount. That's going to be specifically how we think about volume when we think, how do we fill everything in? For right now, we're just thinking, how do we create it? So here's like a picture. You have a circle, and then you're translating it down to, like, let's say the bottom, to another circle. So it's still going to be two congruent circles, and then it's kind of like almost a rectangular part of it here, but it's not obviously straight lines. It's curved the whole way. Okay, so if that's translating a circle, here's another way to think about a translation. Imagine taking a rectangle and rotating it. So rotate a rectangle. If you rotate a rectangle, the best way to look at this is take a rectangle sheet of paper. I'm going to show you an example of one. So let's say we have this, right? We have this rectangular piece of paper, and I'm keeping one part fixed. Like imagine where my finger is here, I'm going to keep that fixed. But I want to rotate this around that fixed spot. And as I go to rotate it then, it's going to form a cylinder, right? So it's going to turn into a cylinder where you're going to have a top and a bottom. You can rotate it like this, like where this part is fixed. You can even rotate it like this. It's just a longer, kind of a skinnier cylinder, if anything, right? So that's another option, rotating a rectangle. And I'll be more specific here, around one side. I'm going to star this right here because there is a question on the test or quiz that will use this idea of how do you create it, you're going to rotate it, and then it may even go on to ask you about, like, well, what would the measurements be? Let's say this rectangle here had a height, I don't know, like a length here of like 10, and then this was 5. Knowing the dimensions of your rectangle, when you go to rotate it about a certain spot, you should hopefully know the dimensions of your cylinder now. Okay, so we're going to practice some of that stuff later on as well. Here's the last two here. We have a cone is another type of solid that it says a solid that has one circular base. It's a cone is exactly what you think you've seen before, like an ice cream cone, right? Here's what it could look like. You have one circle for the base, and then the rest, it's not triangles because they're curved, but they meet at a common point at the very top. Okay, or if you're looking at it the other way around, then at the very bottom, right? But only one circle base, whereas this one had two circular bases that were parallel to each other. And the vertex can't be in the same plane as the base. So, for example, if the vertex is here, the base is at a different plane than it. It cannot be sitting on the base itself because it has to be away from the circular base. Now, to transform this one, you're going to rotate a right triangle 360 degrees about one of its legs. I'm going to actually show you this because I think this is also another one I'm going to star because there could be a question like this on the quiz or the test as well. When you're rotating a right triangle, imagine you have a right triangle like this. Okay, here's my right angle. You would decide which side or which leg do I want to rotate off. Do I want the vertical one or do I want the horizontal one? Depending on what you rotate based on, you're going to end up with a cone that is either have a circular base on its like side or on the bottom, just depending on how you create it. So here, if I rotated based on this smaller side here, I'll even highlight that. So you know that if this is what I'm rotating it based on, imagine it spinning, right? So this right here is going to start spinning so that it forms a circular, I'm sorry, it spun it the wrong way. If this is the part that's spinning here, then this is staying fixed. Yep, and this is where the circular part will go. So imagine a circle there, and this is looking like a cone, like kind of on its side, where the circle is at the bottom, and then the height of the cone would be that part that you kept fixed. Or you can do a different picture here of, let's say I still have my right triangle. This time you're keeping this height fixed, so I don't want to move that, I want to keep it where it is. And as I go to spin this, rotate it this way all the way around, it's going to form a cone looking like this, where you have a circle base, and the original right triangle, whatever that leg was, like let's say it was 3 inches, now just doubled to get this full diameter for this cone. It's going to be a circle on the bottom of it, so we'll figure out the diameter, and the height will stay fixed, whatever that height would be. And if you need to like fully draw the circle around, you can. Okay, so it's a circle for the base, and the rest kind of form up to the top, but they're not triangles. As you can see, they're just curved kind of edges until they meet to the very top. That's why it's different from a pyramid. They look similar, but the pyramid has all straight edges all the way until it meets to the same top. Okay, and finally the last shape, which I'm sure you've seen before, is a sphere. It's just like a ball, or the earth is a sphere. Anything that's a full circular object. It says it's a set of all points in space equidistant from a given point called the center, just like we've learned about just in the last unit with circles. Because it basically, a sphere is like a 3-dimensional circle where you're kind of putting it into more of, giving it more depth. So to transform this, you actually rotate a circle around the diameter. So if you took a circle, found its diameter, and kept rotating it about that, it would create this sphere-looking object, which would be like a ball. And the center, we could label that here. That would be the center of the sphere. So although circles have centers, spheres do too. But we're not going to do too much with the spheres until a few weeks now, because cones and spheres are the only two that we will not find surface area for. We will, however, make sure you know still how do you create a cone, or what is a cone, what does it look like, because you may still have to work with that in the examples. We're about to look at cross-section here in just a second too. Yeah, almost done with this 10.1 part, but the next page is going to show you a little bit about cross-sections right at the top there. And then there is practice if you want to do more practice, but I'm going to, at that point, move on to 10.2 so that we can get through the next part, which I know is extra stuff that we didn't have to do today, but just so we could get through as many as we can before Monday. So a cross-section is the last concept that you need to know about for this introduction, which is it's the intersection of the plane. So in a solid. So what it does is it takes any 3D solid, whatever one you want. Let's say I want to use a cylinder first. And I say I want to slice this either vertically, horizontally, or maybe at a diagonal. I can slice it any way I want. But when you go to slice it, what shape does it create when you're looking at it? The easiest way to imagine this is take, if you could, like a Coke can, a soda can, and if you had a way to like slice through it vertically or horizontally, and then you're looking at it and seeing what shape does it look like. It also helps if you had like Play-Doh or some kind of clay and you had this object so that you could slice it, you could then see some of the cross sections. I may have some models with cross sections. I don't know that I have them here right now, but I'll definitely show you them by next week as well. But it's almost easier to see it in this clear one, if that helps, because you're imagining slicing it in different ways, and as I go to slice it horizontally like this, I would keep getting circles. But if I was to slice it vertically, I would get a rectangle. That's kind of how you're imagining what a cross-section looks like. So these diagrams here say, what are all the possible cross-sections for a square pyramid? Imagine a square pyramid. It's kind of showing it to you. and it shows you all of them. We're going to go ahead and explain these. The first cross section it shows us is that it got sliced this like almost vertically, going straight down. So you have this square pyramid like this, and you're slicing it in a way that's kind of like almost along the same line as that triangle. So you're going to end up with a triangle for the cross section. So triangle is one possibility. The plane that you're kind of cutting through it with is perpendicular to the base. And it has to go through the vertex. You don't have to give it so much detail like this, but I'm just writing this in case you were going to look at it later and wonder, wait, how did that triangle form? It would be if you were to slice this pyramid, perpendicular to the base means up and down, straight up and down, passing through the vertex, you would end up with a triangle for the cross section. Another way you would get a cross section would be a square, because notice the bottom here is a square. So if I just sliced it horizontally, where anything that's parallel to the base, I would end up with a square. So a square would be the plane is parallel to the base. The last one is the one that's the trickiest, and I know that's the one that's hardest to see. It's showing us a trapezoid here, because what happens is if you were to slice at an angle, not straight up and down or straight horizontally, it ends up kind of going slanted through one of the faces, and then creating like you're taking your square and kind of altering it to become a trapezoid. So trapezoid is possible cross-section of a square pyramid, and the reason for that, or how you go about getting there, is the plane is slanted through the base and face. Or I'll be more clear, I'm going to call it a lateral face, which we'll talk more about when we get to the surface area on Monday for that. Lateral face just means like the side triangles that are kind of created. Okay, so you do have lots of practice available if you want to come back and do any of these practices. I'm going to go ahead and move on to 10.2, where we're going to, yep. Yeah, actually, let me get through the first part and I'll get right back to it. Yep. So, because I want to make sure we get time for the second part. There's a lot of practice here, though. If you decide you want some practice of like cross sections, this is a good one, number 4. Like I mentioned, talking about the transformations, we'll maybe try to do some of this on Monday to help make sure we understand what type of shape gets formed, what 3D solid gets formed when you do a transformation from 2-dimension to 3. And then it starts off with this warm-up about like which one doesn't belong. Hopefully as you see these, the one that doesn't belong is specifically the sphere, because it doesn't have bases to it, whereas all of them either have one base or 2 bases. The sphere does not. Okay, so just wanted to quickly go over that one, and then let's get to surface area of a prism and a cylinder. And it's just a little bit longer now, not a whole lot more. But there's one final vocab word before we get to this idea of surface area, and this is a net. The net of an object is a 2-dimensional representation of the faces of a polyhedron. Actually, I'm not going to say polyhedron. I'm going to say 3D solid, because technically we don't have to only work with 3D or polyhedrons. Remember, polyhedrons don't include cylinders or anything with a circle object, but we can technically do nets of any type of 3D solid. And I have a few examples of nets. I'll have more available on that round table I can show you as well. But the idea is, imagine what type of shape would it look like if you tried to put this back together and see what it's made up of. And notice like I have 2 of the same of something, which are like the parallel bases. So this would be either imagining it as a rectangular prism, or it's technically a cube could work as another way. It's just, it doesn't quite look like a square to me. They look more like rectangles to me. But if they were all the exact same measurement, it'd be a cube. Or another way to say that would be a rectangular prism. Because again, you're looking for the parallel bases. Whereas if I have this one, if I look at this example, I have 2 triangles that are across from each other like that. And if I was to try to like put this back together, if it was like flexible for me to do that, where imagine taking paper and like folding it up and then trying to fold it back together, these two triangles would be your parallel triangles, your parallel bases, and then the squares would connect them, or the rectangles or squares, right? So then that would be your net for the triangular prism. So this diagram here is kind of the same thing as what this one is. This one specifically looks like an equilateral triangle or maybe an isosceles triangle, whereas this diagram is a right triangle and it looks like scalene, right? 5, a 12, and then 13. So this is the net right here. And it shows you the dimensions here. And it wants us to, and first of all, you should know what the name of it is. It's just called a triangular prism. Okay, so we have this as an example or this, but just notice the parallel bases. This is a right triangle, this is a right triangle, and they have to be parallel to each other, so like one could be on top and bottom or left to right, however you're looking at it. If you're looking at it like this, they have to be across from each other. You can't have like one triangle in the corner on the right and one on the bottom left. Those are not parallel then. Okay, so that's a net, and there's a bunch of dimensions given here because we can now find the surface area. So the surface area of any polyhedron or of any, really of any 3D solid that we're going to work with is the sum of all, or of the areas of its faces. So when you see a net, you can clearly see what it's creating. The prism is made up of 2 triangles and 3 rectangles. And some of the rectangles are different lengths, that's fine. You would be able to then find the area of each thing separately and then add them all together to get your surface area. Or there will be a formula we can use eventually as well if we prefer to just use the formula that would be on, I think it's on the next page. Because, yeah, I'll eventually kind of summarize the formulas there as well. Because some people prefer to do this in pieces, and some people prefer to just use a formula and plug it all in. You will be given on the test and quiz this setup here, where you're going to be given the surface area. It'll say add up the areas of the faces and bases. You could do that, or we're going to write in the surface area formula here today for prisms and cylinders today. And then the rest will fill in over the next few weeks. Okay, so here's how we could find the different, the surface area given the net here. I could label each of the shapes with a number. So let's just go 1, 2, 3 for the 3 rectangles, and then 4 and 5 are the exact same 2 triangles, right? But I'll just label them so I can account for both. And find the area of each one separately. So the area of the first rectangle is a 5 by 15 rectangle. That comes out to 75. Now I'm showing all my work. You do not have to do this every time. You could just calculate, like filling in the answers even in the diagram. But remember, I can't give partial credit if you don't show anything. You just magically have an answer. And if it's wrong, I can't help you out there then. This next rectangle is a 12 by 15. That comes out to 180. The third rectangle is a 13 by 15. If you needed to label that, that would be 195. Okay, and now we're just left with the 2 triangles. Area of triangle 4 and 5, they're both the same, so we'll just have to add them up twice. But the formula for a triangle is 1/2 base times height, and the base is 5 and the height is 12 for both those triangles. And when I find the answer for that, it's 30, but remember I have 2 triangles, so that's going to be a total of 60 when I'm done between the 2 triangles. So my final surface area, I write it as either SA equals or write surface area equals, and I could just add up the 75, the 180, the 195, and the 60 to get 510. These are areas, so my final answer needs square inches. All right, and that would be it for the surface area. This is what it looks like by doing it like one shape at a time and then adding everything together. Sometimes that seems like a lot of work for people and they don't love that, so that's why I'm going to show you what the formula is on the next page. But on homework and things, you can pick how you want to go about it. Do you want to calculate the surface area separately, or do you want to do it all together? So this this example here, number 1, doesn't tell you the formulas yet. You can come back once you know the formulas and either use that or just find them in pieces for each of the different shapes. And then practice even drawing out some of the nets. Sometimes that helps to say, okay, what is it going to look like when I kind of open this up? All right, and so let's finish up on the next page here. We have just the formulas at the top, and then we'll be all set. So right there it says surface area of a right prism or a cylinder. It's technically saying them together, but I'm going to write each one down separately. Prism, because they are very similar to each other. The prism formula is surface area equals 2 times a capital B plus P. It's a lowercase p technically, but it doesn't matter. And then H. And I will tell you what these letters stand for, because if you're not so sure, we'll make sure we know that. So capital B refers to the area of the base. And that's why this is kind of an ambiguous area, because remember the bases can be rectangles, triangles, squares, pentagons, hexagons, and so on. We're not going to do pentagons, hexagons, and so on because we don't know how to find the area of those this year. But we can stick to any other base that we know, squares, triangles, rectangles, and things like that, right? So we would need to know the area of the base. You would double it, 2 times it, because you're trying to get your 2 bases that are parallel. And then you would figure out the perimeter of the base. P stands for perimeter of the base. So again, you have to know what the base is. Which one's parallel? Is it 2 triangles? Is it 2 rectangles? Is it 2 squares? Find that perimeter of that shape. And finally, H refers to the height. And just to be clear about the height, because people get confused, like, which height are you referring to? It's what's connecting the 2 bases. So let's say we have 2 triangles. It's a triangular prism. 2 triangles, and they're connected by a 10-inch edge, 10 inches between them. That would be your height, or H. And once you put literally everything into the formula, you calculate, you just hit enter, you're done. You just found your surface area. So some people prefer this, and don't forget units, or you could do what we did on the front page where you find each thing individually and add it all together. So a cylinder is very much the same. If we kind of follow the same format, remember that a cylinder has 2 circular bases. So think about the area formula of a circle. It's 2 times pi r squared. Remember the formula of a circle is pi r squared for area. So we just do 2 of those. In addition to that, it uses the rectangular part of it, the hollowed part inside. This would be 2 pi r h. Okay, so if you're wondering, where did that part come from, 2 pi r h? Well, it uses the circumference. 2 pi r is the circumference, and it multiplies it times the whole height of the cylinder to get from top to bottom. So just so that you're good on which part is what, for a cylinder's base, make sure you're using 2 pi r squared, right, because it's 2 times it. And then the perimeter is technically this P is referring to this circumference, and then the H is the same. So if you're trying to match the 2 formulas, they're very much the same. It's just now we're working with circles for a cylinder. All right, so if you want to try an example of doing just the formula and not having to break it down, if I'm given this information here, and that's all I'm told is that it's a rectangular prism, got a height, length, and width of 4. You can, of course, draw a diagram if that would help you. You could even draw the net if you needed to, or you could just use the formula, which would say 2 times the area of the base. Now, you might say, well, which base am I using? They're all rectangles. The good news is you can pick. If you want the base to be the 5 by 11, you can. You could do the 11 by 4. Or you could do the 5 by 4. It's just whatever 2 of your rectangles that you want to start with, then the other number will be your height, right? So if I wanted to use this diagram, and again, I'm not great at drawing these, so do your best. Rectangular prism. Oops, this is a very bad diagram. I'm sorry. Something like this, where it's meeting at the top. If you had a rectangular prism where the base here, let's say, was 11 by 4, because those were the 2 measurements for the length and the width, then that means then the height of the prism would have to be 5, all the way up and down, right? So you would use those different measurements and say, okay, then I'm going to do 11 times 4 here for the area of the base, plus the perimeter of the base would be 2 11s and 2 4s, right? 11 plus 11, 4 plus 4. That would be a total of, and I'll just write it out, 11 plus 11 plus 4 plus 4, times the height was 5. This is one possible setup I could have, and then I could grab my calculator, type the whole thing in, and get 238 square feet. Some people prefer this, but again, this is not the only possibility. I could have done 5 times 4 here instead for the bases and then change that perimeter and the height instead to be the other measurements. But you have to decide what's my base, because rectangles can have multiple rectangles that are parallel to each other, so you can pick, whereas other shapes might be different. All right, I'm going to stop here. I know that was a lot to get through, but if you have questions, please let me know.